So, hello everyone, this is Sayan, and today we are going to study about the first week of our Stats 2 course. Okay, so without further ado, let's get started and let's see that what's in for the first week and let's deep dive for the content. Okay, so the first thing that we have here is joint random variables. Okay, now what does it say? It says that um, when two random variables representing different events, okay, so two random variables, they are representing two different events occur simultaneously, then the event consisting of these two random variables occurring simultaneously is an event made up with the joint random variables. Okay, now what is this? For example, I do have a coin in my left hand and I have a coin in my right hand. Okay. Now I toss these two coins and I define x. Just a minute. What I do is I define x as the value in first coin and y as the value in second coin. And we know that this will take either a success, sorry, either a failure or a success, and similarly y will also take either a failure or a success. Okay, so now when I toss these two simultaneously, then I'm getting an event which will consist of these two variables. Okay, I mean I can get a head for the first coin and a tail for the next coin, or vice versa. So when I'm getting a value that contains two values enclosed in a tuple, because I can get up something like this 0 0 or 0 1 or 1 0 or 1 1, something like this. Okay, so when I am doing this thing, then I'm getting the values for I'm getting the values as tuples. Okay, so when I'm getting these values as tuples and there is not a singular value in here, we can say that these tuples are considered or are made up with joint random variables x and y. This is all that we need to know, or we need to understand about joint random variables. Let's take another example. Drawing, sorry, rolling two dice. Okay. So when I roll two dice, I get some value in the first dice and I get second value, some value in the second dice. Okay, so for the first dice, what happens in here is that when I roll the first dice, I'm getting the value to be nothing but a value between 1 to 6. Similarly, I'm getting for y, I'm getting the value to be between 1 to 6. Now, if I compose an event in which two of these variables are considered, then I'll be getting 36 different combinations. Okay, you can see it in this place. I have already made this. So we'll be getting 36 different combinations. So when we get 36 different combinations, we can definitely think that these two variables, they are consisting an entire event, and hence they are joint random variables because they're occurring jointly for a single piece of event. Okay, so that is something which is known as joint random variables. As I told you, example, rolling two dice, tossing two coins, drawing two balls but of different color from an urn. Yeah, if X denotes the color in the a ball which has been drawn, or the number of green colored balls that have been drawn from an urn, and Y denotes the number of blue balls that have been drawn from an urn, and if I am to compose it into a single event in which I say that x will be 2 and y will be 1. So these two events, these will be occurring jointly. Okay. Hence, this can also be the example of a joint random variable. Okay. Now that's all about a joint random variable and what is a joint random variable. Okay. Now I guess that you can understand what is joint random variable. Now understanding joint random variable is not only important. What's important for us is to understand that how do these joint random variables actually work and how do these actually occur. Okay. So for this case, I have written here that for this case, I've written the joint PMF of two random variables is given as a matrix and is represented for an event as fxy equal to fxy t1 t2 equal to probability of x equal to t1 and y equal to t2. Now what does this mean? X will take the value, sorry um, for this case, x will take the value of t1 and y will take the value of t2. Okay. So this can be written as something like probability that x takes the value of t1 and y takes the value of t2. Okay. This is something that um, consists of the joint PMF. Okay. Now what does this mean? For example, fxy 3 comma 2. Okay. That means probability that, what is the probability that the value capital X, it takes the value 3 and the value capital Y, it takes the value 2. That's all. This is known as the joint random or it's known as the joint PMF of these two random variables. Okay. This is all about the PMF of the joint random variables. Now these are very basic things. Okay. Now we can see that the joint PMF for any or the PMF for any normal or for any distribution, any discrete distribution, this could have been represented as x as, for example, 0 1 2, and then I would have some value probability of x as half half and 0. This is not the case for joint random variables. Okay, since there are two values, notice there are two values, it's x and it's y, they are occurring together. So how am I supposed to represent these values? This value can be represented as f xy. Here it's 1 2 3 4 5 6 and here it's 1 2 3 4 5 6. This is the case when a die or two dice are rolled. How am I representing this? In this table, these values, the values which are horizontal, these represent the values taken by x, and the values which are vertical. Okay, just a minute. The values which are vertical, these represent the values. Why am I not able to get a straight line in here? Okay. These represent the values taken by y. Okay. So this is all that we have to understand, because this is something that we have to represent. And as we know that the two events, I mean, one event is not dependent on the other event. Like if I roll two dice and if I assume that they don't collide with each other, then the number that comes up on the first dice is independent of the number that comes up on the second dice. This is known, right? So similarly, here for this case as well, these two values, or the number appearing in the first dice and the number appearing in the second die, these are independent. So we know that probability of A intersection B is equal to probability of A multiplied by probability of P for independent events. Okay, this is all. Hence, I know that for each and every value, it will be 1 by 6 for x and 1 by 6 for y. So this will be nothing but 1 by 36. And this will be available for each value, because the value that has come in the first place, it can come in the second place as well. We are not putting a constraint that we cannot get the value that has come up in the first place in the second throw or in the third throw or in any consecutive throws after this. So these values can come up, and hence the probability of obtaining each and every value, this remains the same. And since it remains the same, this will be 1 by 6 multiplied by 1 by 6. Hence it's 1 by 36, and it will be for each and every value, as you can see. So here is the pictorial representation for the throw of two dice, and x represents the number on the first dice, and y on the first die, and the value y, this represents the number on the second die. Okay, all right. Now there are some properties of joint random variables. What are those properties? There are two properties. First, sum of all entries in a joint PMF is 1. Okay. Why is this 1? Let me give you a clear idea of that. Look, my entire sample space, the probability that my entire sample space is contained, what is that probability? That will be a certain event. Like, I will be getting an event from my sample space, right? So if I get a value from my sample space, it can be from 1 1, it can be from 1 2, from 1 3, from 1 4, from 1 5, from 1 6, considering that I have this table with me. Okay, it can be anything. Similarly, 2 1 2 2 2 3 2 4 2 5 2 6, 3 1 3 2 3 3 3 4 3 5 3 6, 4 1 4 2 4 3 4 4 4 5 4 6, 5 1 5 2 5 3 5 4 5 5 5 6, and 6 1 6 2 6 3 6 4 6 5 6 6. I can get any value out of these values, but it will be contained within my sample space. So these values being contained within my sample space is something that that will be a certain event. Okay, so probability of S or the sample space is always 1, right? So for this case, if I sum up all these values, then it will be giving me nothing but 1. And you can verify it, because here it's 1 by 36 written 6 times. So it will be nothing but 1 by 6. Similarly, for this case 1 by 6, for this case 1 by 6, for this case 1 by 6, for this case it's 1 by 6 again, and for this case it's 1 by 6 again. And 1 by 6 here, it's written 6 times. And since it's written 6 times in here, we know that for this case, we will be getting 6 times 1 by 6, which is nothing but 1. Okay, it is nothing but 1 for this case. So that's the first property that we have come across for, just a minute. That's the first property that we have come across for a joint random variable distribution. Okay, I hope that this is clear to you people. Okay, all right. So this is the first distribution. The first property. What's the next property then? The next property, it says each entry in the distribution table must belong to the closed interval 0 to 1, and it's very certain. Okay, when can it be 0? Okay, when can it be 0? When an event is uncertain, like not uncertain, it's impossible. For example, I am tossing two coins, and I am expecting that if x and y both take values of 0 and 1, I am expecting that coin to get a value of 2. I'm expecting any coin. Okay, any coin to get a value of 2. How will that be possible? It will either be a success or it will be a failure. Success is represented by 0. Failure is represented by 0, and success is represented by 1. So since that is not possible, so um, this probability will be 0. And when it will be 1, if it tells me that the value uh, of the coin, it can be anything between 0 0 0 1 1 0 and 1 1. So for that case, things will change a little, and it will be like, okay, now first thing can be 0 0, it can be 0 1, it can be 0 2, sorry, it can be 1 0, it can be 1 1. So this is something as of a certain event, hence it will be 1 for the probability. Okay, and now why not more than 0, sorry, why not more than 1 or less than 0? For more than 1, we are dealing with probabilities, and probability, it represents a certain fraction. Okay, so when it represents a certain fraction, how can we expect it to get a value more than 1? It's not possible. You can say to your friend that you are 200% sure that you will be getting some good marks in your exam, but it's not actually mathematically possible. You can be 100% sure, but you cannot be 200% sure, right? And you cannot say that I am minus 100% sure that I will be getting a pass grade in this course. You can say that I am 0% sure that I'll not be getting a pass grade in this course. That's the minimum that you can say, but you cannot say that you are negative 100% sure. Although in theory you can speak out anything, but this is not how it works in the world of statistics. So this is the case. Okay, all right. And this first value, this first thing, it will be put into use excessively, and it will also be put into use for continuous values. It will be integration from negative infinity to infinity, and this also negative infinity to infinity, f x y x comma y dx dy equal to 1. You don't have to actually get all of these things right now. We'll be You'll be seeing it in the coming weeks and in the coming lectures that will be provided by sir. Okay, all right. So this is all about the properties. The next thing, now here we have a question. Okay, what does the question says? I would request you that you grab your pen and paper and you to answer the question, you to solve it, because the aptitude, it gets developed the more you solve. Okay. It says rolling an unbiased or fair die 2 times, the random variable xi follows a uniform distribution from 1, 2, 3, 4, 5, 6. Now what is a uniform distribution? For discrete values and for uniform distribution, we know if x belongs to uniform and x is discrete, then we will be getting some value which will be probability x equals some xi, and x belongs to uniform, say x1, x2, and so on till xn as 1 by n, and I belongs to, sorry, for every xi, for every xi belonging to the range of tx, and 0 otherwise. This is known, and if it's not, then you must know this. Okay, all right. So for this case, probability x equal to xi, it should be 1 by 6 and 0, since it is a discrete random variable. Okay, so xi belonging to tx, this is nothing but the range of capital X, and 0 otherwise. for this case, this will be 1 by 6. Okay, and we are not considering this case because these values are something that don't tell us to consider this case. All right. So xi represents this. Now, what does this mean? Xi is uniform and I equal to 1 or 2. That means for the first throw, there is one variable x1 that will take a value which is a uniform distribution in 1, 2, 3, 4, 5 and 6. And for x2, it will be a uniform value which is 1, 2, 3, 4, 5 and 6. Okay, all right. This is all that xi tells us. Just replace 1 for the value of I to be 1 and 2 for the value of I to be 2. It's as simple as that. Nothing much to worry about. Okay. So for this case, if we consider the value, or if we consider the question, this is something that we have been told to find out, right? We know that it will be nothing but probability that x1 equal to 3 and x2 equal to 2. Okay. And since it's rolling a die 2 times, it means that these are independent events. Like the first roll won't affect the number on the second roll unless the die is damaged. And I'm considering that we have rolled it in the manner it should be rolled. So it's not damaged. Okay. So probability, we can separate this as x1 equal to 3 multiplied by probability that x2 equals 2. And this will be nothing but 1 by 6 multiplied by 1 by 6 because it's uniform for any x. Okay, just a minute. Let's see if we can put, we can put I as 1 and 2. Okay. So this is nothing but 1 by 36. Therefore, our answer will be fx1 x2 3 comma 2 is equal to 1 by 36. That is the answer. Okay. All right. Just go through the solution once again. If you have not understood it, you'll be able to understand it. It's simple. The question is simple. Okay. The second question. From the given table, I have to find the values of f x1 x2 2 comma 2 and f x1 x2 3 comma 2. Oh, sorry. The values have been tangled a little bit. So the given thing is y given x, not y given x, it's y and a bar here x. It is 0, 1, 2, 3. Just a minute. 0, 1, 2, 3. And then it's 1, 2, 3. And it's for x equals 0, 1 by 24, 1 by 24, 1 by 24, 2 by 24, in fact. 1 by 24, 2 by 24, 3 by 24, and then 4 by 24. Then for the value 2, it will be 0, 1 by 24, A, B, and then 0, 1 by 24, 0, 0, 0, 1 by 24. So it's 0, 0, 0, 1 by 24. This is the distribution table. Okay, I've made it here. If you want, then you can, you might not consider this thing. You can look into this one. Okay, all right. Okay, so if this is the question, okay, what did I tell you? I told you that x will be taking, the values that are horizontal, they represent the values that x takes, and the vertical values, they represent the values that y takes. Okay, but this is not our concern for the case right now. What is our concern? Our concern for the case is that how should we find the values of A and B? Because options are given to us, and this can be multiple correct. So for this case, what do we do is, um, we know for the previous property, sum of all entries in a joint probability mass function, it's 1. Okay. So let's do something like, let's add these values. Okay. Let's add each of these values in the table. So it will be 1 by 24 plus 2 by 24 plus 3 by 24 plus 4 by 24 plus 1 by 24. I'm not considering zeros. Plus A plus B plus 1 by 24 equal to 1. Okay. Now let's add these fractions. It's 2 plus 3, 5, 5 plus 4, 9, 9 plus 1, 10, 10 plus 1, 11, 11 plus 1, it's 12. So it's 12 by 24 plus A plus B equals 1. So A plus B is nothing but 1 minus 12 by 24, which is half. Okay. Since when I cut these values, it comes to a total of half. Okay. So I've got a relation from this place, that A plus B equal to half. Now what relation, now this relation will be able to get me the values of A and B. What do I have to do? I have to put the values of A and B for each and every option to check that if they match the right hand side. So let's do that. Half plus half, half plus 0, half plus 0, that's equal to half. It matches my condition, it matches my case. So yeah, this can be a solution. 1/4 plus half, it's nothing but it's 3/4. Okay, which is definitely not equal to half, so no, it does not. 1/6 plus 1/3 is equal to 6, and then it's 2 plus 1, that's 3 by 6, that's half again, which matches my case, so it will be a value. And half plus half, it's 1, so it does not match my value. So my correct options are A and C. Okay, it's as simple as that. You have to just consider the values, the the values, and you have to add these up. This will be from the property 1, that all of these values will be summing up to 1. Okay, all right. Now let's move on to the next thing. Okay, I did keep it because I thought that this thing would be needed, but it was not needed gracefully. All right. Now, it's given to me that the joint PMF of two discrete random variables x and y is given as gxy, x comma y is equal to xy divided by 9 for all x comma y equal to half. Create its distribution table and find the values of probability x plus y equal to 1 and probability x minus y equal to 1. A very important question, and this can be asked because this does seem a little tricky if you do not know the values or the definition. What did we learn? We learned this thing. Now you should be familiar by this thing. So if we did this thing, it means that probability, okay, this is the formal definition. Okay, and this value is something that serves as the entry of each x equal to x and y equal to y value. Okay, and this is given as xy divided by 9. All right. So for x and y equals 1 comma 2 and 1 comma 2, how many possible combinations can I have? Let's see that. X is 1, y is 1, x is 1, y is 2, x is 2, y is 1, x is 2, y is 2. Okay. Okay. All right. So if I have these many combinations for my case, then what I can do is, I can put the function right in front of me, right? So it will be xy divided by 9. What do I have to do? I have to take up the value of x, I have to take up the value of y, I have to multiply them, and I have to divide it by 9, right? It's as simple as that. So my probability here becomes 1 by 9. Probability here it becomes 2 by 9. Here it becomes 2 by 9. And here it becomes 4 by 9. So just a minute. Here it becomes 4 by 9. Okay. All right. So my distribution table will be something like this. 1, 2, 1, 2, 1 by 9, 2 by 9, 2 by 9, and then 4 by 9. Okay. All right. Now I have to find the values of px plus y equal to 1 and px minus y equal to 1. What does this mean? This means that I have to find, for probability x plus y equals 1, I have to find those x and y's which will help me to satisfy this condition. Okay. Now, what I have to do is I have to take each value of x and y and I have to put them in here to see if they satisfy this condition or not. All right. Let's see. For let's make a table. Let's extend the table right here because that will be easier for us to plead the case. Okay. So x plus y and it's x minus y. Not y minus y. Just a minute. Yeah. X minus y. X plus y, for this case it's 2. It's 3. For this case it's 3. For this case it's 3 again, and it's 4. X minus y, for this case it's 0. For this case it's minus 1. For this case it's 1. And for this case it's 0 again. Can you see that for that none of my values of x plus y, they actually sum up to 1? So the probability or the event of me getting a value of x and y that plead my case is nearly uncertain, or it's nearly impossible according to my sample space. I mean, no value between x and y, if they are lying in 1 and 2, can give me my desired result. Hence, it's an impossible event, right? This is an impossible event. And since it's an impossible event, we know that the impossible event probability is always 0 because it has got no chance of occurring. Hence, its chance of occurrence is always 0. Alright. And then, probability that x minus y equal to 1. We can see that from this table, do I have some value of x and y that puts me or that pleads my case? Yes, it does. For x equal to 2 and y equal to 1, I do have a chance that I get my value as 1 for x minus y. Then what do? I do nothing. I do this 2 and 1, and that will be my entry when x is 2 and when y is 1. So this will be nothing but 2 by 9. Hence, this answer is 2 by 9. Okay. That's all. You see, it's very easy. It's very simple. It's just the beginning. And having a good idea of these concepts are very necessary. This one. From a well-shuffled deck of 52 cards, from a well-shuffled deck of 52 cards, 4 cards are selected at random. Let the random variable x denote the number of queens drawn, and let the random variable y denote the number of kings drawn. Find fxy 2, 1. Whoa, a lot of data to process, right? So let's write down. Okay, number of cards in a deck. It's a fact that there are 52 cards. And it has been told to us number of cards drawn, that is nothing but, oh sorry, that is 4 for this case. Okay, all right. So I have to find if X denotes number of queens drawn and Y, this denotes number of kings drawn. Then fxy 2 comma 1. What is this value? Okay, all right. So what do I have to actually do in order to get this value? You see, we do have to remember some facts. What are those facts? The first fact, number of queens in a deck, or number of kings, number of kings in a deck, it's always 4. Okay, so be it kings or be it queens, the number it's always 4. So there are 4 queens in a deck, 4 kings in a deck, and also there are 4 jokers in a deck. These are called face cards. I know, I do believe that you have learned these things in stats 1, because things were discussed in very detail by ma'am when she taught these things. Okay, now what have I been told here? I have been told here I have to find out the value of fxy 2 comma 1. Now what does this mean? This means probability that x equal to 2 and y equal to 1. That means indirectly it's asking me to find the probability that out of the 4 cards drawn, 2 cards are queens and 1 card is king. Okay. So now what I have to do? I know number of ways of picking 50 sorry number of ways of picking 2 cards, or sorry 4 cards from a deck. It's 52C4. Okay, this is known to me by the fundamental principle of counting, whatever you can say, because I'm picking them up and I'm not rearranging them. Hence the number of ways always differ, and it's given by 52C4, because I'm not picking them with some order, like I have to pick some face cards first, then some aces, then some spades, then something like that. No, I'm not doing this thing. I'm not having to do this thing. So this is 52C4. Now number of ways of picking a queen, it's nothing but 4C2, given my favorable conditions are 2. Okay, or I should not say a queen for this case, I should say number of ways of picking 2 queens, and then number of ways of picking 1 king, it is 4C1. And now the number of cards that are remaining, because I have to pick any 4, right? So the number of cards remaining, number of ways of picking up any remaining card, it is nothing but 44 times 44C1. Why? Because out of these face cards, only 44 cards are left for my case, and from these also I have to pick up 1. Okay, So for that case, and if I sum this entire thing up, okay, 44C1. So number of favorable outcomes, it is nothing but 4C2, because two queens have been picked up, and 4C1 because one king has been picked up, and 44C1 because one other card has to be picked up. Okay. And number of total outcomes. This is the number of total outcomes. Therefore, fxy of 2 comma 1, that is probability that x equal to 2 and y equal to 1, it is given by um, 4c2 into 4c1 into 44c1 divided by 52c4. You can calculate this by yourself, since NCR is equal to n factorial divided by r factorial multiplied by n minus r whole factorial. This is a basic and fundamental formula that we all know. Okay. So you can calculate this thing by yourself, and you can tell me the answer in the group. Okay. This is something that's important. Okay. The next topic. What is that? It is marginal PMF. Now, what is marginal PMF? It says it is the sum of all entries corresponding to a random variable, keeping the other constant. Okay. Now, what does this thing mean actually? For our case, let's say I have to get a value, or I've been asked that, okay, you have um, rolled two dice. Okay. Now, for the value of these two dices, for the value of these two dice, I want the probability that my second dice, it gives me any value, but it gives but for yeah, my second dice, it gives me any value, but my first dice, it has to be 1. So what am I doing is that I'm fixing the first dice as 1, or I'm fixing x equal to 1, and then I'm traversing through the entire spectrum of y. And that is the fundamental definition. That is what I have written here. Okay. And this is explained clearly by the formula, which says probability x equal to, it says, what am I doing? Yeah. Px of x equal to summation of pxy x comma yj and yj belonging to ry. What is ry? Ry is the values y can take. Okay. Okay. So this is something that I have fixed capital X for a value. Sorry, I have fixed capital X for a value small x, and now I am running through the entire spectrum of y, fixing that one value of small x. Okay, this is something that the random variable or the marginal distribution, it tells me, and this is for x. Okay, you can see that this is for x. Sorry, very much sorry. This is for y. Okay, because I fixed the value of x here. Okay, and x takes the value of x. This is something that you should remember, and this is also written as fx of x. Similarly, for py of y, it means what is this? This is the marginal of x. And what is this? This is the marginal of y. Okay, all right. What does this say? It says pxy. I'm running through the entire spectrum of x, and I've fixed y. Okay, I've fixed y, and this rx, this signifies that values that x can take. Okay, that's all. That's enough. Now let's do an example. Again, it has got some glitch in here. So what I can do is I can write this column here. Sorry. Okay. What is this? Fy t2. So this is the marginal of x, right? Oh, just a minute. I've messed up a bit. It is the marginal of y. Okay. It is the marginal of y. So if I'm asked the marginal of y, it means that I have to fix x. And if I'm asked the marginal of x, then I have to fix the marginal, and then I have to fix the value of y. Sorry, what did I write here? It's again marginal of y. It's marginal of x. Okay. So here for fyt2, if t2 takes the value 0, what should I write here? It's 1 by 4 plus 1 by 4. So it will be nothing but half. If t2 takes the value 1 here, so what are the probabilities that I can get? Either it's 1 0 or it's 1 1. Okay, so this will also be nothing but half, because 1 by 4 plus 1 by 4. For odd case we use plus, we use addition, right? So it will be half. Similarly, if t1 if t1 takes the value of um, 0, then what values can I have for y? I can have the value as 0 0 and 0 1. Okay, so it can be written 1 by 4 plus 1 by 4, which is half again. And similarly, this also 1 by 4 plus 1 by 4, this is half again, because 1 0 plus 1 1, this is half. Okay, all right. And one thing to notice, that since it is based on one variable being run through its entire spectrum, keeping the other constant, it will always sum up, the values or the entries will always sum up to be 1. So be it from this part or be it from this part, it will always be 1. We have a question in front of us regarding this. So that's the main reason because of which I had to tell this thing to you. Okay. Now, what does the question say? Okay, maybe I have messed up a bit in these things. So the last three columns are, sorry, the first three columns are actually the last three ones. So we'll be traversing it accordingly. Okay, all right. So if I have something like, let me just copy the value. Um, to new page, and then let me move it a bit upwards. Yeah, yeah, this should do. Okay. So I have been told to find the values of k, a, b, and c. Okay, all right. So for finding the value of k, either I can traverse the entire spectrum of x, keeping y constant, or what I can do is I've got a simple solution for this. See, I can do something like I'm keeping k as constant here, and I've told you that since it's a PMF, so all the entries of these PMF will be ultimately equal to 1. So what I can do here is k plus k plus k plus k is equal to 1, or 4k is equal to 1, or k equals 1/4, or k equals 0.25. Okay, that's all. That's all for the value of k. Now, regarding a, what do I have to do is I have to fix the value at 1. I have to fix the value of t1 at 1, and then I have to traverse to the entire spectrum of t2 to get the value of a, as I told you from the previous example. So a for this case is 0.02 plus 0.05 plus 0.02 plus 0.12, and that is nothing but 2 plus 5 is 7, 7 plus 2 9, 0.21. Similarly for b, I have to fix the value at 4, and then I have to traverse downwards to find the value of b. So let's do that. It's 0.07 plus 0.05 plus 0.08 plus 0.01. So 7 plus 5 12, 12 plus 8 20, 20 plus 1 0.21 again. Alright. For c, what do I have to do again? For c, I have to fix the value at 5, and then I have to traverse through the entire spectrum downwards. Why am I saying this? So that you get used to this thing, you get used to this methodology, and you can apply the same during your exams. So it is 0.06 plus 0.08 plus 0.05 plus 0.01. So it's 8 plus 6 14, 14 plus 5 19, 19 plus 1 20. So 0.20. So the values of A, B and C are 0.21, 0.21 and 0.20 respectively, and the value of K is 0.25. Okay. Now it's not necessary that the values of K will be constant. This is by an instance that we got the values of A to be constant, but it might be that the values of K will be variable, but this methodology should always work. Okay. And for this next thing, we could have also done the same, like I could have found out A, then B, and then A plus B plus some value of then 0.21 plus 0.21 plus some value of C plus 0.20 plus 0.18, that is equal to 1. I could have done that thing, but it's easier for us to understand through this method, I believe. Okay. Now let's jump into conditional distribution. These things right now are very easy, and I must admit that they are easy as hell. What is conditional distribution? We have studied that probability A given B is probability A intersection B divided by probability of B. Okay. Now replace the event A with the random variable x taking some value x, and replace the event B with the random variable y taking some value small y. So this is nothing but probability x equal to x, small x, and y equal to small y divided by probability of y equal to small y. So this is all. Okay. And we know that if something like this is given, it means that probability x equal to small x, and or if I can convert it into my normal functional value, it is fxy x comma y divided by fy for a given value. So what is this? This is joint distribution for any value of x and y divided by marginal value. Okay. Now, had it been y equal to small y and x equal to small x, it would have been nothing but it would have been fx of x. Simple as that. Okay. Now, why don't we find out something like, why don't we get some examples? We have been given our table right in front of this place, and again, the columns have shifted, and I don't know how or why, but I don't care. We have understood how to decode this pattern, how to decode this Da Vinci code. So, given this thing, given this table to me, what do I have to actually do? I have to, let's say I have to find the value fx equal to, fx and y, given y equal to 0 for 1. Now, what is this? I didn't say this thing. For conditional distribution, we represent this entire thing as fx given y for a value of x, and this is y. Okay. Or for this thing, we can represent fy given x equal to small x for a value small y. Okay. All right. So, if I have to find out this value, what does this mean? It means probability x equal to 1 and y equal to 0 divided by probability that y equal to 0. Okay. So, for this, again, what can this value actually be? This can be fx y 1 comma 0 divided by fy 0. So what is fxy 1 comma 0? For t1 belonging taking 1 and t2 taking 0, what do I have to what do I have here? It's 1 by 4. So it's 1/4. And fy0, that means for the value of t2 being 0, okay, I have to traverse through this entire list, or I have to traverse through this entire sequence, and I have to add each of these, and then I'm given a value of half after adding these. We have done it in the previous example, right? So it will be 1 by 4 divided by half. So now chop chop, it's half. And that's all. That's all that we have to know about conditional distribution. Okay. All right. Now, this thing. We have done this, but still, for the sake, if something like fx given y of x is given, we have to traverse the entire spectrum of x and then give the value. And for fx given y equals y, we have to traverse the entire spectrum of y. Basically, the marginal thing. Okay, you don't have to bang your head on this thing. You'll be doing it. You'll be able to do it once you start practicing problems specifically. Okay, all right. Now, this is something that we don't get usually, but if it's in here, then it's better to actually understand. Conditioning with multiple random variables. Look, when you'll be training your models in data science or in machine learning, you'll be having multiple events that will be occurring. Okay, and now you have to train your model with many constraints, right? So, what you have to do is you have to train your model in such a way that this constraint, that one constraint is followed, then other, then other, then other, and you will be having many constraints on your favor. So, for this entire set, if I assume that this is my entire machine learning model set, that is the event, and these are my constraint, so I have to train the machine model accordingly. And how do we do it? There is one simple formula, there is one simple thing that we have to keep in mind. It's joint of x1, x2, or the joint of the entire event that is given in the left hand side before the bar, divided by the joint of the entire event that is given after the bar. Okay. And we won't get questions based on these. We won't get much questions. So it's pointless to bang our head on this. But since it was given in the syllabus, I thought covering it would be simple. Okay. And it is indeed simple. Like you have to just put the values and you have to find the values. Given you'll be given a very big table for 4 or 3 values. Okay. All right. For example, if I have to find out x1, f of x1, comma x2, comma x3, given y1 equal to 3, y2 equal to 1, and y3 equal to 2, and 0, 1, 0 for some event, it will be f of x1, x2, x3, 0, 1, 0 divided by f of y1, y2, y3, 3, 1, 2. That's all. Okay. Just I took an example so that you can understand the entire. Okay. All right. Now there is a question regarding this. What does the question say? It says that the joint probability mass function of two discrete random variables, capital X and capital Y, is given as fxy of x comma y equals x plus y divided by 36 for all x comma y belonging to 0 comma 1 comma 2. What is the value of probability 0 given 0 less than x less than 2 given y is greater than 1? Now how do I solve this? We are given fxy of x comma y equal to x plus y divided by 36. Okay, this will be capital Y. So we do get confused. People do get confused. In fact, I did get confused for this. Okay, and x comma y, x comma y, they take the values 0, 1 and 2. Okay, all right. So if I construct my distribution table, what do I get for this case? X here, y here, and then it will be 0, 1, 2, then 0, 1, 2. So 0 plus 0 divided by 36, that's 0. 1 plus 0 divided by 36, that's 1 by 36. 2 plus 0 divided by 36, that's 2 by 36. I'm not simplifying it. I'm not cancelling out the terms because maybe I do need it in some way or the other. Then 0 plus 1, that's 1 by 36 again. 2 by 36. 3 by 36. 2 by 36. 3 by 36. And then 4 by 36. This is my probability table. Okay. And if I have to find out the if I have to find out the marginal for each of them, specifically for y, okay, then if I have to find the margin of x, so fx, fy of y, that will be 3 by 36, 2 plus 3 5, 5 plus 1 6, 6 by 36, 4 plus 6 7, 7 plus 2 9, that's 9 by 36. Okay, all right. Now I have to find probability 0 less than x less than 2 given y is greater than 1. That is probability 0 less than x less than, what did I do? Less than 2 and y greater than 1 divided by probability y greater than 1. Okay. So for this case, let me see. X cannot be the only value that y greater than 1 satisfies, it's 2. Okay. And the only value that 0 less than x less than 2 satisfies, it's 1. So indirectly it's asking me this thing. I mean, discrete is easy. For continuous you have to integrate and whatnot. Okay. Divided by probability y equal to 2. Now what should I do here? Let me convert them. Fxy 1 comma 2 divided by fy for how much? 2, right? Yeah, 2. So for 1 comma 2, That means x will take the value 1, y will take the value 2. So it's 3 by 36 divided by fy2, it's 9 by 36. So it's 3 by 36 multiplied by 36 upon 9, chop chop, chop chop, it's 1 by 3. So this is the answer. As simple as that. Okay. And probably with this, we come to the end of our lecture. This is all that you have to study in week 1. And do revise all the questions that I've given you. And do revise the notes in order to get a better clarity. So thank you.